Here is our sample problem today. We've done problems in the past on horizontal springs and storing energy with a horizontal spring. Now we're going to vertical springs. And my favorite vertical spring situation is a bungee jumper because I went bungee jumping sort of once when I was okay, it's not even sort of. I need to pause the video and tell the story to everybody, and then I'll come back and explain the problem. Alright, so story's over. It wasn't very good. Anyway, so the idea is we are going to be bungee jumping. That's what I was starting to describe. And with this bungee jumper, they're going to fall at first from here to there. And what we just talked about with the class is that a bungee cord is actually just like a gigantic spring. It behaves exactly the same way. It behaves like a linear spring as long as you don't stretch it too far. And if you stretch it too far, that's the least of your problems. So, as in, you're probably not coming back up and you're hoping it doesn't break. So that would be really bad. But as this bungee cord is coming down here, it follows this whole first 8 meters, the X and L, the natural length of the spring. It's going to follow that whole distance without ever stretching. So you're just going to have 8 meters, which is about 25 feet of just free falling. Then the spring starts to stretch, and as it stretches, we're going to figure out first stretching to the equilibrium position, and then keep on stretching right on past there down to D, where D is our maximum stretch distance. And so our speed down here at D is 0. This is the farthest we're going to go. Alright, in this setup, what we want to think about is what forces are acting on us in different places and what our system should be. So our system can either be just the person, or our system can be the spring mass system of the person and the spring. When we look at the energy conservation, we'll look at the spring mass system, but when we're drawing free body diagrams, we'll just draw them for the person. So as the person's falling at first between A and B, so from A to B, our free body diagram would just be the person with gravity acting on them. Between B and C, so in between here, as we fall to the equilibrium position, that person's going to have 2 forces acting on them. They're going to have gravity, and they're going to have the force of the spring. And later on in this problem, we'll talk about which of those 2 forces is greater in between here, in between B and C, so from B to C. And then from C to D, as that person continues to fall, we're still going to have forces acting on that person. And again, it'll still be gravity, and it'll still be the spring force, but we'll think about which of those 2 is greater, and thus how that controls the motion from C to D. Okay, so our system is that, and I just went ahead and drew all the free body diagrams to help us with this. Alright, the things I'd like to know are what is the speed of the person when they're at the natural length, so what's the speed when they're at B? Where will the maximum speed occur, and why? So that's more of an essay concept question. Might involve some free body diagrams. What's the maximum speed going to be? Wherever that happens to be, what is the actual maximum speed? And then what's the maximum distance stretched? So this X down to D, that's really my X maximum. That's what I'm trying to find. Okay. If we're like the other class, we'll get through parts A, B, and C during this bell, and then part D will be made in yet another video. But maybe if we're lucky, we'll get through this whole thing in one video. I don't know. Alright, so the first piece. We drew our free body diagrams, and in all of our pictures, there's 2 forces acting. There's gravity, and there's the force of the spring. When we look at those 2 forces, we always have to decide, are they conservative or non-conservative forces? Okay, and we said with muttered exuberance, conservative. Yes, so they are conservative forces acting on this thing, or on this person. So since they're conservative, we know that the mechanical energy at any of these places, at A, at B, at C, at D, the mechanical energy has to all add up to the same amount. Our overarching theme for all parts of this problem, the idea we're going to be using again and again and again, is mechanical energy at some location plus the work done by non-conservative forces is equal to the mechanical energy at some other location. And these 2 locations can be any place in this whole setup. You get to pick where you're comparing to where else. Alright, so we're going to think for a second first about what 2 locations would you want to compare to do part A to figure out your speed at the natural length. And then as we're doing that, we also then will set up where we think our original height is going to be 0. So I'm going to pause, talk to the class, and we'll come back. Alright, so our class chose to compare the mechanical energy at A to the mechanical energy at B. And as we said before, the only forces acting on us are spring and gravity, and those 2 are both conservative forces. And so this work done by non-conservative forces, that's an a subscript NC, that's 0. There's no friction, no air resistance that we're worried about. Apparently this person has a similar preferences in bungee jumping as I do, where I like to bungee jump in an airless vacuum. So good enough. There's no air resistance to worry about. All right, the second part with this then. We want to think about the different kinds of mechanical energy we can have at A. So our different kinds of energy are gravitational potential energy, kinetic energy, and spring potential energy. And that has to equal our mechanical energy at B, where we've got the same three varieties: gravitational, kinetic, and spring potential, also known as elastic potential energy. All right, well, with those three chosen, how much energy we say of any of those three kinds that we have depends on what we choose as our reference point. So for the spring potential energy, we have no choice. Our spring potential energy, as soon as we start stretching our spring, so as soon as we go past the natural length of the spring, we start storing spring potential energy. But along here, from A to B, we're not stretching the spring, so we don't have to worry about spring potential energy anywhere from A to B. So spring PE, this is going to be 0, because we didn't stretch the spring yet, and this is still going to be 0. And since it's like a rope, we don't have to think about it as being like compressed at all. Okay, gravitational potential energy, where we say we have 0 gravitational potential energy, depends on what we use as our reference height. So again, think about where you would like to choose as a reference height. I'm going to pause the video while we talk about that, and then I'll tell you what we picked. All right, so our class, we voted, a lot of people chose A, but even more people chose B, so we're going to choose that the height at B is our height of 0. If you don't like that choice, you don't have to stick with us. You can always choose height at A, just realize that's what we're going to do. You can choose height of A as 0, and then all these will just be negative potential energies, but gravitationally speaking, but that's fine. Okay, so if that's the case, then if this height is 0, then we have no gravitational potential energy at B, and since we are bungee stepping, not bungee jumping, we have no kinetic energy at A. We're just kind of stepping off the edge. We don't have any speed initially. So this problem simplifies quite a bit. This becomes mg height at A is equal to kinetic energy 1/2 m velocity at B squared. And then let's start solving. So the mass of the person, at least for this section of the problem, cancels out. And we get that 2 times g times the height at A is equal to velocity at B squared. So this is 2 times 10 meters per second squared times the height at A, which is 8 meters up. Okay, so 2 times 10 is 20, times 8 is 160, and then VB is going to be the square root of 160, which I would guess, if I was just estimating, is somewhere around 12.5, but it turns out to be it's like 12.65 meters per second. So that's how fast we're going at B. An important side note, someone said, well, could we have just done kinematics? We could have just done kinematics from A to B at least, because the acceleration is constant, but not from B to C or B to D or any of those other ones. All right, next piece for us. We're looking at, now, part B. Where will the maximum speed occur and why? So I'm going to pause the video, let our groups discuss, and then we'll come back. All right, so we posed this question to our group, and everyone in our class thought that the maximum speed was going to occur at one of 3 places. Either at B, so at the natural length, between B and C, or at C. Nobody thought it was going to happen there, where only gravity was acting. Nobody thought it was going to happen here, where they felt like the spring's force would probably be too large. Okay, so we just need to figure out why it is the right answer, or which one is the right answer and why. So we're going to do that by looking at free body diagrams. Going from A to B, the only force we have acting on us is gravity. So you're going to accelerate at a constant 9.8 meters per second squared, which will round to 10 meters per second squared, all the way from A to B. At B, now you start to stretch that spring. So there are 2 forces acting. There's the force of the spring, and there's the force of gravity. But as we're stretching, how do these 2 forces compare in size? Which is larger, force of spring or force of gravity? Gravity. Okay, so since gravity is larger, this person is going to continue to accelerate all the way down until they get to the equilibrium position. Because until equilibrium, where at equilibrium gravity is equal to that force of the spring, until there, this gravity is still bigger than the force of the spring, so you still have a net downward force, so you still keep getting faster. Okay. Past equilibrium, that force of spring is bigger than gravity, so you begin to slow to a stop until down here you actually do stop and shoot back up the other way. So your maximum speed occurs when you stop accelerating in the downward direction, which occurs at C at equilibrium because that's the place where those two forces become balanced. So for part B, Vmax occurs at equilibrium for what we just explained. Okay, now we got to go on and try to do part C. So part C says, all right, well now you know where the maximum speed occurs. Now you've got to calculate how big that speed is. So to do part C, we want to start off by thinking about this in the same way we did for part A. Part A. For part C, we still want to do some comparing of energies. Apparently the class did not anticipate that part A, but it certainly just happened. So, all right. So we're comparing the same kinds of energy. We just got to pick two places to compare. One of them has to be location C, but you can choose where you want your initial location to be. And again, too, our work non-conservative is still going to be 0 because we still don't have any friction or anything, and only gravity and springs, and those are both conservative. So, as you're sitting there at home, you can decide, do I want to compare the mechanical energy at B to C, or do I want to compare the mechanical energy at A to C? You also can make the choice, do I want to keep this as my gravitational potential energy 0 location, or do I want to shift it somewhere else? All those are your choices. Spring-wise, we have to choose the natural length of the spring as 0 spring potential energy. So, all right, so I'm going to pause the video. We're going to have some discussions about what we're choosing for this class, and then we'll come back and go forward. All right, so for this video, this is a little different than the other class we just did this with. They're going to compare the mechanical energy. Oh boy, that's just so convoluted. They wanted to go comparing the mechanical energy at A to the mechanical energy at C, but use B as our reference point. We can do that. We'll do it anyway. So we're going to say we're going to compare the mechanical energy at A to the mechanical energy at C, but we're going to use B as our height of 0, gravitationally speaking. Now, somebody in this class, we'll just say Maya, pointed out that, you know what, to be able to do this, you need to figure out how far you need to know where XE is. You need to know where that equilibrium position is. Well, we can solve for that, and we probably should. We said the maximum speed occurs at equilibrium. Well, we know that this is true at equilibrium, that the net force acting on the object has to equal 0 at equilibrium. There are two forces acting on us at equilibrium. There's the force of the spring, so F subscript S is the force of the spring, minus the force of gravity has to equal 0. That force of the spring is K times X, because it's a linear spring. And that force of gravity is mg. So that equilibrium position, X subscript E, E for equilibrium, just equals mg divided by K. This is what you were doing when we did that lab. You were finding the equilibrium position. So M for this person is 40 kilograms. This is a very light person. This might be Stu from the bungee jumping fame of my youth. This G is 10 meters per second squared, and we're dividing that by K, which is 4 hundo newtons per meter. So 40 times 10 is going to be 400 divided by 400. This is conveniently 1 meter is the equilibrium position. All right. Then we want to compare the energies at A to the energies at C. And when I say energies, I mean different forms of spring potential, kinetic, and gravitational PE between those two locations. And I always find it's a good idea to write out this term or this step and then just cancel out whoever's going to be 0. So as I'm looking at this, there's a couple different kinds of energy that are 0. Let's see. At A, I don't have any spring potential energy because I haven't stretched the spring yet. So that's 0. At A, I don't have any kinetic energy yet because we're not moving yet. And at C, at C I have all three kinds. Ooh. Okay, so not a whole lot of Zeroville going on there. All right, at A, I have a potential energy of m times g times height at A, where the height at A is measured from here up. At C, I have spring potential energy of 1/2 times k times the equilibrium stretch squared, so that distance squared. I have kinetic energy of 1/2 m velocity at c squared, and that's our maximum speed. And this is the kicker, I also have gravitational potential energy of m times g times the height at c. Okay, in those, we're ready to start plugging in some numbers. So the mass of, well, actually let's do some algebra first. We're trying to get this v by itself. So let's algebraically solve and get that v by itself. I'm going to pause the video while you do the algebra. Alright, magically lots of algebra just appeared on your screen. And the one thing to note in this, all this is just what numbers I plugged in. I quit putting units on it because I was going to run out of space. Sorry. And then this height at c, notice that I made it -1 meter because c is 1 meter below our reference height. But it spits out radical 170, which is like 13.03-ish meters per second. So that's our maximum speed. Okay. To do part D, we're going to have to do that in a separate video because this video is already 16 minutes long. So I'm just going to stop this one here, and then we'll go from there.